Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy them. So check out Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And don't forget to go to dataengineeringpodcast.com/chat to join the community and keep the conversation going. Your host is Tobias Macy, and today I'm interviewing Bin Fan about Alluxio, a distributed virtual file system for unified access to disparate data sources. So Bin, could you start by introducing yourself?
Yeah. Hi, Tobias. My name's Bin. I'm glad to be here. So I'm right now the founding member of Alluxio company and also the PMC member for Alluxio open source project. I was working on the project for about almost 4 years. And before I joined the team, I was working in Google on a large scale distributed systems, storage systems, very similar to in the same space as Alluxio. And before I joined Google, I was actually a PhD student in Carnegie Mellon working on distributed systems and focusing on storage systems. So I've been working in this space for a while.
And do you remember how you first got involved in the area of data management?
It's from my early PhD years. So actually, maybe it's on the third year, I start to look at key value systems, key value storage system as part of my PhD thesis. So I was involved in we hacked actually a lot into Memcached at that time to emphasize on memory efficiency and throughput. So we had one paper out of that. And then I actually, because my work on that, I visited UC Berkeley AMP Lab, where I get to know the founder of Alluxio, Haoyun Li, who was a PhD student in UC Berkeley AMP Lab at that time, because he is also working on similar like in-memory storage. Yeah, so in the same space. So we know each other, and then after that, he got because I graduated and just go to Google to work. And Haoyun Li, he continued studying in UC Berkeley, and finally his research project was funded by VC and created this company. And so he called me, and actually I picked up the call, and I feel like this is a very interesting and very exciting opportunity. So I just quit Google and joined Alluxio. So yeah, that's my whole story.
And as you mentioned, Alluxio started its life in the AMP lab at Berkeley, and I know that it was originally released under the name of Tachyon. So can you give a bit of an explanation about what the Alluxio project is and anything additional in terms of the history of how it was created and how it has come to be an open source Apache project and the organization that you've built up to support it?
Yeah, so this is a great question. So in the early days, it was a research project called Tachyon at that time. Actually, it has even less known name before even Tachyon. But in the Tachyon days, it was open sourced from the very beginning. The motivation for having this project is actually heavily related to Apache Spark. I think at that time, Spark is already taking off from UC Berkeley, and a lot of people are looking at Spark, and they see the great potential for this new computation framework, aggressively using memory. So one complaint people always have is, even at that time or even now, memory is still considered as a maybe more expensive storage resource than the other storage capacities. And Haoyun Li, the founder of the project at that time, was taking a look at this project, and he found it can be more efficient if you have a system external to Spark and let different Spark jobs or different Spark contexts to share data more efficiently. So that's how, in the beginning, he started this project, and actually he open sourced it. And gradually, this becomes more like a general purpose file system, distributed file system, rather than just one sharing or caching layer for Spark, but also for other computation frameworks like Presto, like MapReduce, or even TensorFlow in the new days. So that's how basically the project is evolving. it starts as a very specific purpose, just help Spark to manage the data more efficiently, but gradually becomes a in-memory file system, because this in-memory file system needs to handle data persistency. Because the first thing, once you talk about something in memory, the first thing people are asking is, what if if you restart the machines and you lost data from memory, how do you deal with this? So from the first day, Tachyon or Alluxio at that time is designed to handle this kind of basically data persistency issue with even volatile storage media like memory. So this is very fundamental to the design for this system and becomes fundamental in the architecture. If you compare Alluxio with other distributed storage systems like HDFS or like Google File System from the paper. So I would say this is like something fundamental to the entire ecosystem, to our entire design. And it turns out very interesting in the days, especially nowadays, people are talking about separating storage and compute. Storage is getting can be far away from the compute, because the storage can be some cloud storage. And in this case, having Alluxio works perfectly in this architecture, because we can be in the middle between compute and the real persistency story, since we are not targeting to solve this data persistence issue. Long story short, I think we start from a caching layer for Spark using memory to a general purpose file system. It's a file system. It's not a caching system. A distributed file system with the awareness of some other, we call understores, to provide data persistency. So the architecture becomes different from 10 years ago when people are talking about, oh yeah, we should move compute to storage. Let's have deeply coupled storage and compute. And we build open source around this idea. We have more than 900 contributors from all over the world joining this project because they want to contribute, for example, the adapter to read their own data source, their own persistent data store. And we have a lot of interfaces for people to customize, so they have different cache policies. This open source project is getting more and more popular, and we also provide an enterprise offering. So the core features in terms of all the things I mentioned so far are in the open source edition, what we call community edition. We also provide, so as a company, we also need to survive. We need to have a business model around this open source. So we provide enterprise offering, which adds more enhancements in security or in like large scale or high availability, this kind of enterprise readiness features, like owning a lot of these large corporations they are looking for when you run services in their environment. Yeah, so this is our business model.
And a couple of the things that you mentioned in there preempted some of the questions I have, particularly in terms of the persistence of the data in memory, as far as what happens when you have a memory failure in a machine or the instance gets rebooted, and how that data distribution gets managed, at least in terms of the long-term persistence of the data, where you rely on the underlying storage systems to provide those guarantees. I'll probably have a few more questions later on about how you manage distribution among the Alluxio layer once the data has been retrieved. But before we get into that, I want to talk a bit more about some of the use cases that Alluxio enables, because as you mentioned, there was a big push of moving compute to the data because of the inherent gravity that these large data sets have. But as we move more toward a cloud-oriented environment where you have these object stores that don't have any guaranteed physical location, so you have varying levels of latency as you're accessing these object stores, or if you're trying to run in a hybrid cloud environment where you have your own local data centers, and then you're also trying to interface with public cloud for bursting capacity or for taking advantage of some of the specialized features that they offer. So, yeah, going back again, just wondering if you can talk about some of the use cases that Alluxio enables that would be impractical or sort of too difficult to want to deal with without it.
Yeah, great question. The first case I would recommend to explore is really if you have data remote from the compute, and we see cases like people are having a different data centers, and they have cross data center traffic to load data because you want to do a join, and one table is in one data center, and another parts of the computation, other tables are in the local data center. So in this case, having Alluxio in place will help greatly to reduce the computation time, because you can either preload the table from the remote data center to the Alluxio caching layer, or Alluxio have the intelligence built in to bring the data on demand. And next time, after the code read, next time if you read the same data again, this will be cached locally. So we do see a great performance gain in cases like this. So we have published use cases with Baidu, the search giant in China. They see performance benefits by 30x in these cases. See, the other case, interestingly, I see more is really the cloud, as you mentioned. So actually, this is also what I observed. The companies of the new generation, they typically born on cloud. They start from AWS or Amazon or Azure on the first day. And even the older generation company, they have aggressive plan nowadays to move their either data or compute or both to cloud. And once you are moving to cloud, the natural storage choice for you is, for AWS is S3, right? But S3 is awesome. I like S3 a lot. It's cheaper compared to other storage capacity, and it's scalable. It's very easy. The semantics is very simple. It's very easy to manage. It's a single global namespace. However, there are also costs come with all the convenience here. For example, once you have all your data in S3, your compute, if it's say on EC2, will naturally always drag the data from S3 to your local compute engine. So this will go across network. And S3 sometimes has different semantics compared to the traditional file system. For example, the rename can be expensive, and also listing a huge bucket, a bucket with, say, thousands or millions objects inside can be very slow. So in these cases, people do want to have a more familiar or more traditional performance implication for the storage service. And also the new trending machine learning applications, they emphasize a lot on iterations. They take data from last iteration and do some computation and output to the next iteration. And from that on, the data from previous iteration may not be important at all. So these kind of you need a temporary data store rather than some persistent data store. So we see cases on running computation on cloud. They want to have a caching or another tiering on top of the cloud storage provided by the vendors like S3 or Microsoft. And Alluxio can fit perfectly in this case. So I named two cases. I think there is a third case, which is very interesting. I see mostly from users in China, the internet companies in China. They like to do a topology that I have a centralized main HDFS data source, but because my HDFS service is heavily loaded, because we have giant number of different applications depending on this data. So what we see is, to guarantee the SLA, they also set up we call satellite clusters, and each cluster is maybe a zone just for one specific computation service, for example, Presto. And in this case, the data and compute it's still in the same data center, but it's still cross different machines, go cross network. And because they have seen issues with high pressure on their HDFS service, so they see, okay, let's put another storage here, co-located with my satellite compute cluster, and mirroring the data in the main storage. And we don't need the whole set, just need the working set, right? So Alluxio work perfectly in this case too. So we see a lot of use cases around this, especially for internet companies in China.
And so can you talk a bit about how the Alluxio project is implemented to allow for these data reflections and high performance access of data, particularly in the face of varying levels of latency, whether it's the case of interfacing with cloud object storage or the situation that you just described where you're using it as a way to keep a working set accessible to a compute layer that's remote from a centralized Hadoop or other sort of data lake that it would be too large to keep in memory of the compute instances, but is manageable by an Alluxio cluster without having to pull the entirety of this set of data from that central data lake.
Yeah. So as I mentioned in previous question, Alluxio was born actually in the beginning to solve challenges like this. So there are a few things we are doing to help reduce the latency and reduce the performance variation, the retrieval latency variation. One thing is we aggressively use memory as the main storage media. So although we provide optional choices, you can use Alluxio to manage memory or optionally SSD plus, optionally hard disk. But we still see a lot of users use Alluxio to manage memory which has a higher bandwidth when you have a very hot data inside. And also, we have done a lot to provide what we call short circuit data read and data write. So essentially, we aggressively leverage data locality. For example, if there is a distributed application, for example, it's a Spark. And the Spark, if it's using HDFS interface to access data, it will try to allocate the tasks closer to the storage. And this is by having some APIs to understand where are the nodes serving this data. So Alluxio, if it's deployed co-located with a Spark or other computation framework, we also provide a similar compatible interface. And in this way, we will try hard to match the task to our workers serving the data. In this way, they don't need to go cross network to fetch the data. So memory and data locality. And also, so the third part actually is related to metadata. So Alluxio is not just a data caching layer. We also, as I mentioned, this is a file system. So we have our own dedicated metadata service. It's a file system. So we maintain the inode trees and all this journal, all these basic elements required for a file system. That means if you have a slow list operation on S3, that will happen once. But after that, Alluxio understands how the metadata is on S3, and we will serve this instead of having S3 to serve this metadata queries. So by doing this, we can reduce even the operation variations on the metadata side.
So, to your point about the tiering of storage, where your primary operations are being done in memory, but you have the capability of also using the local disk on the Alluxio nodes, I'm wondering if you can talk a bit about the lifecycle possibilities that you have as far as managing when the data gets moved from one layer to the other in the Alluxio nodes, but also as far as aging out data that you are accessing where it gets initially pulled into the working set by a request from the compute engines, and then at some point it is no longer relevant, or if you need to page out data because more data is being requested than can be held within the Alluxio cluster, just how that overall tiering and lifecycle management happens within the Alluxio layer itself.
This is also a core feature provided by Alluxio. Essentially, from very high level speaking, you can think Alluxio is a cache. It's a distributed cache for file data. So each Alluxio worker is the component handling all the data capacity, really provide data capacity, and then you can add more or n different workers into the cluster. Each Alluxio worker implements a cache, and by default, we use LRU as the caching policy. We also make this pluggable. So in addition to LRU, we have some other policies built in, and we do see users provide their own caching policies, replacement policies too, because they understand their workloads better. So that's on the caching side. On the other side, we also provide functionalities for users to actively control the data life cycles. For example, we provide commands. You can set a TTL for a file or a directory. Say, I set the TTL to be 1 day. Then after a day, the data in Alluxio can be freed. It's up to the workloads, but we do not guarantee it's in memory anymore if you set a TTL. And there are also policies like I want to really ping this data in memory layer. So that's another command you can use to really put the data in the top tier and closer or faster to the computation. So so that's basically what we do for the life cycles. And we are actually looking at more complicated different policies in the future because we do see, especially for enterprise users, they have a more sophisticated lifecycle management requirement. But right now, these are all available in open source community edition.
And as far as being able to manage the life cycle of the data in the underlying systems, where, for instance, you might have initial data getting loaded into S3 from an inbound data pipeline, and then you do some analysis or processing on it, and then you want to store it more long-term in your data lake, or maybe vice versa, where it's coming into your HDFS cluster, and then you want to store it long-term in S3 or some form of cold storage. Is there any capacity in Alluxio for being able to manage that lifecycle, or would it just be based on the mount points for those underlying storage systems and then having the computational framework be responsible for reading from one location and then writing back to a different mount point for that more persistent long-term storage and archival?
This is a great question. And we this is basically what I mentioned. Like we do see large enterprise, they have requests like this. They really want to have a very intelligent data management system to migrate data from hot storage to warm storage, and from warm storage to cold storage to improve data efficiency and not to reduce their data cost. And right now, with the current Alluxio open source edition, what you can do is just mention like you can write ETL jobs to move data from one location to another, like if they are backed by different mount points and representing different under storage. So that's possible doing that. And we don't have automation on here yet, but I believe this is on the roadmap in the future.
And another question I have, particularly as it relates to metadata, is in a computational layer, if you're trying to search for either a particular set of records or just do a discovery process of seeing what data is available in which systems, does Alluxio proactively retrieve the metadata from those storage systems so that those initial, for instance, LS of the file structure return more quickly, or does it do a fetch at the initial read time and then just cache it for a particular period? And then also, I'm wondering if it has any native support for some of the more high-level data storage formats such as Parquet or Avro, where you can potentially query from the computational layer into the underlying files to determine if a particular set of records has the information that you're looking for before you necessarily retrieve it into the Alluxio layer for further processing.
This is another great question. Go back to the metadata question part first. The both mode, like loading the data on the first operation and loading metadata on the first operation and put it into our metadata store. And also, you can also, the second mode is you can also preactively load metadata. Like if you know my computation will touch this bucket in the next hour or so, let me just try to run something first to preload the metadata. So both are supported. And in terms, so this is how the metadata enters Alluxio and being remembered by Alluxio. And remember, and regarding how we manage the life cycle for the metadata, we also provide different policies. For example, you can set a cache expiration time. The metadata I remember for this tree, for this part of the file system, will be true for maybe an hour, and later on we will just do another load once some application is accessing data there. So this is one policy. The other policy is, so there might be out of bounds modification to my under store. Frequently, let me just don't trust all the cached metadata. And on every single operation, I need you to check the update on the understore site. So there's another policy to be very aggressively. But we do see this will, you can see that this will make the metadata operations slower because it's just adding more overhead. So it really depends on the application. And we also adding new features so that for certain end stores like HDFS, there are hooks you can put. Once there are some modification to their metadata, you can register some action on their site. So we can just proactively update the metadata once there's modification there. So I think this is also something we will do in the new feature in the new release. So the second part is regarding how we can optimize. Maybe if we understand more about data structure in the file, like Parquet, or do we do some push down? So right now, Alluxio is a file system, so we understand the data format as just a very plain bit stream here. So we do not go into the file structure to put more to provide more optimization. But on the other hand, I'm working with actually some researchers from universities and to see if I know this is a Parquet file, and can I do something smarter? For example, can I do some clustering, or can I do some more intelligent replication? Yeah, so that's something I think it's a very interesting direction, and we will see how the result goes.
Yeah, and another possible approach to that would be to rely on other metadata storage systems where, particularly for Hadoop, where you have something like the Hive Metastore or the Iceberg table format that's being worked at in Netflix and with other people, where you can potentially interface with those metadata storage systems that are already doing the work of parsing the records within those more high-level storage formats, and then be able to use that to determine which subset of files have the information you need to then retrieve into Alluxio.
Yeah, that's definitely another way to go. And we are very interesting to see the some if there's some experimental result or some benchmark. So we are very interested to see that and see if we can just influence the roadmap for Alluxio in the future. And I think this is something very interesting, and I hope this can because it's open source project, university researchers or some other people, if they feel this is something worth doing for their workloads, and we are very happy to provide some help or some collaboration and on this end.
And in terms of the actual code itself, I'm wondering if you can discuss some of the particular challenges that you've faced in terms of building and maintaining and growing the project, and discuss some of the evolution that it has undergone in terms of the overall architecture and design of the system.
Yes, I have a lot. So I just share one interesting story. My first big project in Alluxio after joining the team is to make Alluxio modularized. So if you know a little bit more about Java, JVM applications, so Alluxio is built in Java, like 90, maybe 95% of source code is written in Java. So the way it works is you just build Alluxio into jars, different jars, binary jars, and JVM will just execute the jars. So in the early days, because it's a research project at that time, and developers or maintainers for the project were really looking for fast growing, right? Just like move fast. So everything, all the components were in the same single Java module, which means you compile a single jar. Even it's on the client side, you put it into Hive or you put it into MapReduce, or it's also the jar you execute the service, you provide the RPC service, provide the daemon, long running daemons. And this is really a bad design, but it gives a lot of convenience because like the Java in Java land, because it's in a single module, you can reference all the other classes without worrying about managing the dependency. And my first project on Alluxio is to break this a single monolithic jar into multiple jars with a clean dependency, so we can distribute a much thinner jar to applications like Hive or MapReduce or Spark. And it takes me quite a few, I would say, months to figure out the relationship between all these dependencies, callers, and then figure out the way to break this into multiple different frameworks, different jars, different modules. And so one lesson I learned from there is once the project starts to grow to a certain degree, we should start thinking about architecture much earlier, so we can have a much better management in terms of all the dependencies, and this will simplify the life down the road much easier. And after that, actually, we are pretty happy with the structure, but still after adding new features, more modules come in, and how to make this plugin pluggable, and how to make different components very easy to upgrade. It's also it's forever going process. So that's something regarding the source code management. And also as a Java, if you work in the Java land, you will understand the Jarhao issue, which is the pollution of the binary libraries on other applications class paths. And it's particularly a challenge for us because we are supposed to talk to all different kinds of data stores. So originally we just put everything together on the class path, and then you will see all the dependency how issues. We spend a lot of time to dealing with that, and you have to do a lot of dirty work in workarounds or hacky ways to solve these Jarhao issues. So later on, we decided to do this in a very clean way and use the class loader to isolate the libraries. So in this way, we see much less issues in terms of Jarhao, but it also makes the code a little bit more complicated. But I think this is totally worth it. Yeah, code-wise, this is something also we learned, very, very important. The other part, I would just one last thing is really the resource management. People know Java, Java is a good language because you don't need to handle you don't need to delete something you allocated from the heap, like the garbage collection will help you to be lazy. This is only one part of the resource. There's a lot of other resources. For example, the sockets you open, the logs you acquire, and especially this can be a distributed log. And also, for example, all the file handlers, all these different pieces, and even sometimes for efficiency, we also use the lower level Java APIs, and there can be memory leak related. So how to handle this well to make sure you don't leak the resource? So in the beginning, we all because it's a distributed file system, right? So once you have these kind of issues, it's very hard to debug, to diagnose. And once you know that, it might be relatively easy to fix. But even to diagnose the issue is very hard. So what we later on decide in the source code we do is to really have a very strict pattern, like everyone should just follow this pattern when you acquire some resource. And we leverage some good things from Java. They provide some good functionalities from Java they provide to make sure once you quit, like normally this resource will be returned. But also, for example, if you encounter some exception, so you don't really expect, you go through the code path you don't really expect. We make sure in that way we also return the resource correspondingly. So this also helps a lot to make the source code much more robust.
In terms of being able to write it in such a way that you can easily add new backend capabilities for interfacing with different storage systems, and also making it easy for different computational frameworks to interface with Alluxio, what are some of the particular challenges that have come up on that front? And what are some of the trade-offs that you've made in order to be able to provide a single API to the computational layer that works effectively across all of those different underlying storage systems that might have varying capabilities or more advanced functionality that's not necessarily exposed?
Yeah. So one challenge, as just mentioned, if you want to talk to different underscores, usually they require different different libraries, and how to make all the libraries to work together happily. So as I mentioned, we use the class loading to isolate all the dependencies to make all of them happy. And also the other part is how to find a common API so that it's useful enough, and also it's common enough, and to cover all the different storage types. And we do have multiple iterations on top of that, right? So in the beginning, we have one set of API. So we call this understore API. And later on, we realized this is not sufficient, especially when we see more use cases with object store. And the object store has very different semantics, not just the semantics, but also like a security, all the security requirements with the traditional file systems. So we do put a lot of emphasis on that to make it work. So I think after multiple iterations, we gradually converge to a version that works for most of the cases. This is something we call to the southbound, basically how Alluxio talks to the Ender store. We also have the API we call the northbound API that's what we provide to different applications. And we on that side, most of the applications we see so far use our Hadoop compatible API. So in that way, applications can just assume this is just a Hadoop file system. This is just a different implementation for Hadoop file system. So they can continue use whatever they assume, but just replace Hadoop HDFS with Alluxio. On top of that, we also have our own API, file system API, which is more similar to the Java file system API, and adding more features like setting TTLs, doing the mount, and doing a lot of Alluxio-specific functionalities. And one interesting trend we see nowadays is, in the beginning, it's because people have their legacy. They want to run their legacy applications on the distributed file system. So they want the POSIX API. So we do have a contributor from I think it's from IBM contributed the POSIX API for us. But later on, then we just realized actually a new generation of the machine learning applications, they leverage aggressively heavily on POSIX API. So they typically assume the data is on the local directory. So this becomes now popular again among these machine learning tools. So but essentially the way we handle the northbound is we provide different set for like HDFS compatible for distributed application like Hadoop or Spark, and more traditional applications or even a new wave of machine learning applications, we provide the POSIX API.
And from the operational perspective, I'd like to get an understanding of what the different scaling factors are in Alluxio and some of the edge cases that come up as you try to add and remove nodes, particularly as it relates to data distribution within the cluster.
Great question. We see a few different, depends on the workloads and the environment, we see different scalability factors here. The major one is really the bottleneck on the master node. Our master node, you can think it's equivalent to Hadoop file systems name node. And because the master node is using on-heap Java memory to store all the mapping from file to maps, from inode trees to different detailed information. So these can be very memory hungry. And also this can be GC intensive. If there's a lot of small intensive modifications to the file system. So this becomes one scaling bottleneck once you store, say, hundreds of millions of files into Alluxio namespace, and becomes a unstable part for the metadata service. So in the new release, in the next coming months, we're having the new 2.0, whole new 2.0 release. We are moving this part, the on-heap memory for file system information, basic file system inode tree, to a off-heap implementation on that. And by doing this, we can scale the file system to be much larger, like contain billions of files and directories. So this is one thing. The other part is really how many workers you can handle, because there are heartbeats between workers and master, and there are different communication the control message sent over. So if you scale to thousands of nodes or beyond, you will see the master node becomes a bottleneck, or at least very pressured because of this kind of workloads. So one way we handle this is we testing this aggressively on release to make sure we can scale to thousands of worker nodes. But also we optimize a lot on the RPC side, threading pool, all these different things. So we really want to make it work. I think in the new release, we can handle at least a few thousand workers in one deployment. So these are the efforts and the bottlenecks we have seen in terms of scalability and our efforts to improve on top of it. So what's the other part of the question?
Just wondering how scaling the node count up or down impacts the data distribution in the cluster. So I'm wondering if you use things like consistent hashing to ensure that you're always able to retrieve a record from a given instance, or if you use more of the name node style approach where you have metadata in the master about where all the files are located, and then also any sort of redundancy so that if one node does go away, you don't then have to retrieve the data all over again from the source system and can instead just replicate it from within the Alluxio cluster.
Two parts. One is on the metadata service part. We do provide high availability mode. You can run multiple master nodes, master service inside Alluxio deployment. And we internally, we use Zookeeper, and in the next release, in the coming release, we're using Raft to decide who is the primary master node serving the metadata service. And also on the data side, we do have replication scheme built. So this is actually something very interesting I want to highlight. If you think about the HDFS, the default replication factor is 3, meaning we want to have this data 3 copy to avoid we lost data in some time window. So that's the replication factor. And in us, because we are not aiming to provide persistence, so we do not have a target. By default, we do not have a target replication factor. It really depends on the workload, the temperature for the data. For example, by default, if the data is hot, then the application may just trigger more access to retrieve to data, and turns out this will make more replications in Alluxio space cached into different workers. So in the coming release, we also provide replications. So you can set, okay, I want the minimal set of replication to be 3 for this data copy, or maximally this can be 10 copies, and beyond that, I don't really need more. So more fine-grained control on the replications against fault tolerant failures. And also regarding the consistent hashing, as you said, we use both. We use the master node to remember where the data is located across different workers. But on the other hand, we have a policy that when we load data into Alluxio, to avoid some skewness, data skewness, we can also specify a consistent hashing something similar to consistent hashing way to place the data, so we can get a more uniform distribution across in Alluxio space when we drag in data into from the data source. And you can set, okay, I want replication to be 3 or 4, and then even you have 10 different workers reading the same data, and they will not compete too much for the understore bandwidth, and also this will guarantee the 4 or 3 copies you specified are uniformly distributed. Basically, they will coordinate.
And when I was looking through your documentation and blog posts to prepare for the show, and I was impressed that you consistently run testing and verification at scale versus just making sure that you can execute a certain set of unit tests and then rely on users or beta testers to ensure that new releases are bug-free and are not subject to regressions. So I'm wondering if you can talk a bit about your overall approach for being able to run these verifications at scale, and also any operational considerations that you've built into Alluxio to make it easy to be able to build and deploy these clusters in an automated fashion.
Yeah, we put a lot of emphasis on that in terms of testing and also the ease of deployment. So regarding the testing, there are multiple different levels of testing happening. So first, we because I'm from Google, I used to work with Google, and in my team in Google, we emphasize a lot on unit tests and integration tests. So I try to, when I join the team, I try to bring the same mindset. And we do have requirements for the unit test. Anyone who contribute the code will ask, okay, can you also write the unit test, and also, if possible, get an integration test too. So these are built in with the source code, coming with the source code. Once you try to submit something to our GitHub repository, these tests will be automatically triggered, so we can have some sanity check. But later on, we realize, okay, this is not sufficient, especially after a few releases. We notice if some issues will only be identified if you're running this service for a while. like 4 hours or 4 days or even 4 weeks. So what we do is we build more tests. We call it nightly integration, nightly test, which we write the whole entire infrastructure on AWS to like launch these tests nightly, so we can run different workloads, including high bench, including TPCDS, or more micro benchmark, like just pressure the master node or just pressure the worker node and see what's the result in terms of performance, in terms of correctness. So we do have nightly build too. And before release, we have more strict tests, like in more complete test suite for the release. And also we will ask partners, friends, or users, heavy users in the community to help us test the beta in their environment. Even that, bugs are always, there will always be bugs, right? So we will also try hard to help users to get the bugs fixed in the first time, in like immediately. So we just recently launched the Slack channel, so we can talk to the users more in a more real-time fashion. But also we talk to these users like periodically to check out whether they see any issues. If they see any issues, we will just try to solve them, help them to solve these issues earlier. I think all these are actually common practices from different industries and companies, and we just try to implement it in our own, suiting our own team and our environment, and it works pretty well so far. And regarding the scalability test you mentioned, that's something we were very proud of. Like, we are doing these tests with thousands of worker instances to really pressure test our service. And we do spend a lot of efforts on this to make it affordable cloud, because we always use AWS or the cloud infrastructure to build our tests. So as I just mentioned, we have a blog on that, and we actually have a white paper summarizing all the caveats, and we see when running this scalability test on AWS. And I think it's a really good read.
And going back to the deployment topology, as you mentioned, the primary use case is for being able to provide data reflections so that you can get faster access to some of these underlying storage layers, and possibly at a remote location in the case that you described with the Chinese internet providers. So can you discuss a bit about what the typical topology is in terms of how Alluxio is deployed in relation to the storage systems, and particularly with the compute? I'm wondering if you have the compute operations running directly on the same nodes that Alluxio is using, or if they're just co-located from a network perspective.
So we have our recommendation to co-locate Alluxio with the set of nodes running Alluxio to be the same set of nodes running the computation, for example, Presto or Spark. So in this way, you can trigger what we call the short circuit data I/O, data read or write. And so they don't need to go through, because we try to aggressively leverage data locality. So if they happen to be on the same node, you don't have to go through network. So that's the recommendation for topology to deploy Alluxio. We also see cases that Alluxio is not really co-located in the same set of nodes due to a variety of different reasons. And in that case, it really depends what's the bandwidth and also what's the latency from your compute to your data source versus your compute to Alluxio deployment. If it is still a large ratio, meaning even it's not on the same set of machines, but it's within the same rack or same data center, versus the remote data source is really remote, it's across the ocean, or in that case, I think that's still considered as close enough, and that's basically what we see. Essentially, the recommendation I would say is make sure Alluxio is close enough to the compute compared to how the data source is to compute.
And for somebody who's planning a deployment of Alluxio, what should they be thinking of in terms of system capacity, as far as RAM that's available and disk that's on the system, whether it's spinning disk drives or SSDs, and any sorts of optimizations that they can make either at the node or network layer?
The system requirement is not really, I would say, for the master, it depends on the master or worker node. For our metadata service running on the master node, you probably want some relatively beefy nodes with enough memory, or say like on the order of 10 to 100 gigabytes. So you can have enough space to store the file system information and making sure you don't really see a lot of GCs. For the worker nodes, it really depends on your target SLA. If you're really targeting a very strict SLA, returning data in a very short latency compared to reading from disk, then use Alluxio to manage and to allocate and manage memory for you. But if you're really dealing with the SLA to reduce your target, if your target is really reduce the latency of reading data from a remote data center, in that case, I would say like having Alluxio to manage SSD or hard disk is already good enough for really good enough for the workload. Because in that case, having data in memory versus having data on local SSD or a disk do not really provide like significant gain. On top of that, you already reduce the network latency by removing the part dragging data from a remote data center. So that's my philosophy to set up Alluxio deployments.
And what are some of the cases where you would recommend against using Alluxio for a given use case? And I'm curious if there are any other projects or products that are working in a similar or possibly adjacent space that might be a better fit for those situations.
There are cases we think Alluxio is not really the best fit, including if you have your database is your source of truth, and Alluxio right now is integrating with the file system or object store more, and database is not really one available or ready to use data source for Alluxio. And in that case, having Alluxio in between is not really, I don't think that's the target use case. And another use case we think is not really a good fit for Alluxio is if you have already co-located computation and storage, and your network bandwidth is awesome, and your hard disk bandwidth is also has no pressure at all, like or your memory is a lot, then from time to time we see there's also marginal benefits running in this case, but we do also see some other benefits if you run in the co-located case. Like, I mean, when I say co-located, I mean the data source is already co-located with the computation. So we do see use cases by putting Alluxio again in here for SLA, because different applications are competing for the disk spindles and they do see large variance, but serving data from Alluxio memory will just increase the data bandwidth. But if that is not a problem, then in the co-located environment is not our target use case. Let me see. The similar or adjacent space, we do see, for example, there is a product called S3 Guard. That is really more like a cache for S3, but that is only for the, I think that's only for the metadata part. So if you want to cache data, that does not provide you. So Alluxio does both data caching and metadata management. So S3 Guard is one way to translate S3 APIs, the object store, into a file system API for different applications to consume. But that's only on the metadata side. And there are also some projects we see doing similar, but only on the data path. They do not handle or they do very straightforward translation on the metadata side. For example, Hadoop itself, you can use Hadoop to access S3 directly. That's no problem, but it's just doing a client-side translation and use some different client to access S3. And there will be no data caching and no metadata caching either. Yeah, so and also we see cases they do only data caching, but not the metadata management. So I think we see a few GitHub repositories providing functionalities like this. Essentially, they just use a local node. Once you read from S3, and you just put this data, you download it from S3 to your local node. And once the same node requests data, you can just serve it from local storage. But this is not a really distributed. There's no coordination between the local cache. So this is very, I would say this is very single node, and there is no coordination to help applications to access data from a different cache on a different node. So yeah, so my takeaway is our project is pretty unique. I guess one of the reasons is in the early days it was a research project. So we just do whatever we think is interesting to do, and later on it turns out has real use cases, and it turns out solve real important problems for users, and it's open source, and I think a lot of users just take it instead of having launch a new similar project.
And what do you have in store for the future of the Alluxio project and company?
So in the near future, we are releasing Alluxio 2.0. As I mentioned, there are major upgrades to Alluxio, including we're moving inode trees to off-heap storage. So this is something we are doing. And also we are changing the entire RPC system to be more scalable, more extensible, and a lot of new added features like async propagation from Alluxio space to the data stores. So that's really in the near future, in a few months. And in the long run, Alluxio is really, we just want to be the unified data access layer for any applications. And now we start from big data world. And in the future, we hope this can cover like different other areas for different workloads. For example, we start to also see more and serve more machine learning workloads. And so we just go across more areas. And also, we used to see only people use big data or mostly use big data for unstructured data. But nowadays, in the last few years, definitely people build more systems to derive insight from more structured data, like, for example, Presto or Spark SQL, all different big data SQL query engines. That's also becoming a trend we see, and we hope we can have more deeper integration with these kind of systems. As for the company, we are still early stage, I would say. So also in the early days, we focus a lot on engineering, and now we think open source is something we really want to focus in the community. I mean, the user community is something we really want to focus in the next few years to help really understand how users are using Alluxio and understand how we can help users to improve the value. And actually, I'm part of the effort. And if you need any help or see you have any interesting ideas, feel free to talk to me, and I'll be very happy to have more discussion.
And for anybody who does want to give you that feedback or follow the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think one actually very important change in the last few years is really the trend moving data to the cloud. And I will say this is something you see every maybe 10 years, such a huge change. And cloud cloud storage vendors, they just provide their own mostly object store service with some file system wrapper on top of that. But still, we are still in the early days to learn how to build a right architecture when you really move your computation to cloud, or either public cloud or on-premise cloud. When this happens, how do we really architect the system well? And based on this new architecture, which means the computation and the storage are more and more disaggregated, then what are the different new possibilities, and what are these toolings associated? Like one thing you mentioned, how to automatically migrate data from hot to warm, from warm to cold storage. And also, for example, in the future, can we have even a smarter way to decide which cloud storage vendor I should pick based on the price or based on the topology? So all this data management, I just see we are entering a new era that we are able to do a lot more things. And I think this will take a few years for us to really understand what are the new things we can do in this new era.
Well, thank you very much for taking the time today to describe the Alluxio project. It's definitely a very interesting platform and one that seems to fit a very big need in the big data community. So I'm happy to see the work that you're doing on that. So I want to thank you again for your time, and I hope you enjoy the rest of your day.
Yeah, thank you so much, Tobias. I'm very happy to share my experience.